Hello everyone, I am Andalib and I am right now a PhD student at Iowa State University, and today I am going to discuss about the impact of sensing range on the performance of real-time traffic signal control. Now, several of the real-time adaptive traffic signal control algorithm uses arrival table, which is basically a record of expected vehicle arrival time. Now, previously, most of these researchers used advanced or upstream point detector data to prepare or predict this arrival table. Now, it is actually the point detector data only provides presence or absence data, but the real-time vehicle trajectory data can be an alternative, and it may be the prediction may be more accurate. Now, connected vehicle can actually provide this type of trajectory data, but it is no, we are not sure when or how what would be the penetration rate of connected vehicle. So LiDAR, radar, or video detector can also provide similar trajectory data, and so we can actually have even now this type of algorithm implemented in network in real field. Now, all of these sensors are actually limited in within a distance, and we can refer this distance as the sensing range. And if we actually look at the literature, there are many methods available on the real-time signal control, but there are actually very few on the discussion on the impact of sensing range. So our study actually seeks or explores further the what would be the impact of sensing range on the performance of signal control. Now, the control scope for real-time adaptive traffic signal is actually limited to planning horizon domain and the enhanced actuation domain. In the planning horizon, usually the algorithm plans for the phase timing and sequences. And in the enhanced actuation based methods, it is actually limited to whether to extend or truncate the current phase. Though the enhanced actuation based method is not the optimum one, it is time efficient. Also, in the planning horizon period, it is not likely that it is actually going to implement all the phase sequences and timing, but rather it implements the first few seconds or the first few seconds of the planning horizon. And that first few seconds here is called the head, and the rest of the part is called the tail. At the beginning of the tail period, the algorithms actually usually recalculates all the optimization decisions. Now, for this purpose, we actually took one algorithm from the trajectory for the planning horizon domain and another one from the enhanced actuation domain. And the phase allocation algorithm is from the planning horizon domain, which was originally developed by a group of researchers from University of Arizona. And the enhanced actuation based algorithm was developed by the self-organization algorithm, which was developed by a group of researchers from Northeastern University. And both algorithms use an estimated arrival table. Phase allocation algorithm is basically a bi-level optimization where in the upper level a dynamic programming approach is used, and the dynamic programming approach in the upper level usually sends a barrier length information to the lower level function, and in the lower level function based on the barrier length it actually optimizes the phase duration and phase sequences, and sends this back to the upper level program, and the upper level function also stores this information. And later a backtracking algorithm was used to retrieve the optimal plan. Now, phase allocation algorithm have a planning horizon length of 2 cycles, but the head part is actually limited to the first barrier length. So the algorithm runs in once per barrier. And for phase allocation algorithm, coordination is considered as a fixed priority request. Now, self-organizing algorithm has actually two different self-organizing actually based on an efficient actuated control, and later it allows secondary extension for progression along the arterial. Now, for efficient to make the actuated control more efficient, we have used advanced detectors along with the stop bar detectors. So we also used minimum green time, maximum green time, lane by lane detection for gap out logic, and non-simultaneous gap out, and also flashing yellow arrow for backup prevention. Now, for self-organizing algorithms, secondary extension part, it is actually allowing the platoons in the major arterial and extension period extension when the major arterial gaps out. Major gaps out. So what is happening here is that it is basically taking some time from the non-arterial phases and allowing this time to the arterial phases. And what is this doing is it is causing a very small delay in the arterial phases, but it is actually making sure that the arterial phases platoons don't have to wait for a very long rate period. So this is the main idea. And the larger and denser platoon, it is more likely that they will get a secondary extension. And the possibility of allowing a secondary extension depends on number of vehicles, headway, volume saturation ratio, cycle and difference between adjacent intersections. Now, we also compared these advanced algorithms with conventional algorithms like fully actuated control and actuated coordinated control. In the fully actuated control here, conventional, we didn't use any advanced detectors, and the actuated coordinated control timing plans were optimized through synchro. Now we implemented these ideas on a 3-intersection corridor in VZIM. All these 3-intersection corridors were 8-phase, and all the left turns were protected permitted. And algorithms were coded in Python using COM interface, and virtual SC3 controller were also used, and calls are placed via detector channels through COM. To implement self-organizing algorithm, it was to implement self-organizing algorithm, it was basically the ordinary fully actuated control, and dummy detectors were also used to hold on phase calls. And for phase allocation algorithm, the timing decisions were supplied by phase allocation algorithm itself. Now we also use 3 different volume scenarios. The first one is the symmetric volume, which uses a balanced main line, and the cross-street traffic is substantially lower. And in the asymmetric scenario, one direction is heavier on the other in the major arterial, and cross-street traffic is also again substantially lower. In the balanced volume, the cross-street traffic and the mainline traffics are quite similar. Now, if we look at the results for the total delay, we can see that the performances of the both self-organizing algorithm and phase allocation algorithm delay decreases with higher sensing range, and fully actuated control actually performs quite similar to the advanced algorithms. This is actually understandable because it is very difficult to beat the performance of fully actuated control. But it is not always the goal of signal control to minimize total delay, but rather sometimes it is the focus is actually to allow progression through arterial. Also, we can see that the algorithm actually converges at around 1,000 feet for self-organizing algorithm, at around 1,500 feet for phase allocation algorithm. Now, if we look at the arterial versus non-arterial delay, we can see that the self-organizing algorithm actually have kind of a V shape. This is understandable because the self-organizing algorithm was initially taking the time from non-arterial phases and giving it to the arterial phases. So initially, even though it shows some improvement, gradually non-arterial delay decreases. Also, self-organizing performance is quite similar to the fully actuated control, and the phase allocation algorithms performance is similar to the close to the coordinated actuated control. This is also understandable because phase allocation algorithm plans for phase sequence and phase durations, and also plans for the next 2 cycle, whereas the self-organizing algorithm is kind of on full actuation based, so the performances are close to the fully actuated control. Also, phase allocation algorithms performances in both direction decreases as increases higher sensing range, but the rate of convergence is actually higher at with higher sensing range. Now, if we look at the travel time frequency diagram, we can see that the fully actuated control performs worse, and the coordinated control sometimes performs better, and mostly the resolution algorithm performs better. But in the asymmetric eastbound direction, the self-organizing algorithm actually performs worse than the fully actuated control. And typically, self-organizing algorithm have better performance than the self-organizing algorithm. Also, the sensing impact of sensing range is very clear from here, as the higher sensing range has more reliability than lower sensing range. Now, if we look at the coordination diagram of signals, we can see that the fully actuated control has a percentage of green time around 41%, whereas coordinated control have 78%. Also, the phase allocation algorithms performs very good in terms of progression, and it is actually percentage of green is actually ranged in between 72% to 76%, which is pretty low for self-organizing algorithm, which is 42 to 53%. But it is still better than the fully actuated control. Also, the cycle length and phase durations in self-organizing algorithm gets better with higher sensing ranges, and similar is actually in the phase allocation algorithm. There are occasionally very small cycles, but with higher sensing range, these things is not very common. Now, what is our final finding is that with trajectory-based signal control method that actually performs better with increased higher or higher sensing ranges, but occasionally we found some inconsistency. And with lower sensing range, both the algorithm were actually underutilized, but above 1,000 feet both the algorithms perform better, but their performance, which one is actually better in between these two, it depends further on the volume configuration. And above 1,500 feet both the algorithm converges or show little benefits with increased ranges. So this is our findings, and thank you everyone for listening to me.
Thank you for the opportunity to present here. Today I'm going to present about the calibration of traffic simulation model using high resolution controller data. So why do we use the micro simulation model? Because micro simulation is very adaptable to the increasing complexity of the transportation network, and we want to replicate the stochastic nature of traffic flow, especially when we are modeling the arterial network. And in this case, calibration is a critical component for to replicate the local traffic characteristic. We want to ensure that microscopic parameters are realistic to the field performance evaluation, and for that we use here advanced and emerging data technology to model the driver behavior parameters. This study uses high resolution control data combining with clustering technique for scenario identification and multi-objective optimization technique for the VSIM model parameter calibration of the arterial network. So we use the emerging data source such as high resolution controller data, which is the event-based data, and the data resolution is 0.1 second. That means that in every 0.1 second we get a status of the field condition, especially in the signal condition, that and the conditions are coded in two parameters. One is event code and one other is event parameter. So from there we can access to different kind of performance measures of the signal controller, such as turning movement count, actuated phase timing, the green occupancy ratio, and split utilization ratio, also percentage arrival on green, and many others. So utilizing these performance measures, we at first separated the actual field traffic condition using clustering method. And the clustering method was performed in two level clustering. One is at first the travel time data was categorized, 24 hours travel time data was categorized, and from there we see that there is peak hour, off peak hour, midnight and midday scenarios are separated. For each scenario, for example, maybe peak hour data, we again clustered them based on green occupancy ratio we derived from the high resolution controller data. So these clusters were also have another level of, at first it was two movement clustering, and then for each two movement the cluster was based on the left turn movement, so that each patterns have distinctive field per field scenarios which has the how much left turn or two movements are two movements have the green occupancy ratio for a specific time of the day. So for each scenario, for example, here this is the cluster for travel time. For travel time, the travel time, actually the cluster was based on the eastbound westbound direction travel time, and we see that in eastbound direction there was more travel time in the morning peak hour, and the westbound direction the travel time was more in the evening peak hour, and there are some midday travel time, and also in the morning like 12 a.m. or 1 a.m. this kind of data. So we take one of the cluster. For example, if we take the AM peak and then cluster the green occupancy ratio for two movements and left arm movements, we get the category of different traffic operational condition. So for each operational condition, the PC model was generated, and we didn't want it to mix up different kind of traffic operational condition so that we get a perfect microscopic parameters later. So for one of the category from the clustering method, we manually coded the VSIM model, and we manually calibrated the vehicle inputs, and we coded the TOT plan. We also manually fixed the desired speed distribution and also reduce speed areas, all of these things. And after that we wanted to calibrate the driver behavior parameters based on the field data for the local condition. So we use the genetic algorithm and also multi-objective optimization, the another version of genetic algorithm, which is NSGA3, which takes more than two objective function in the equation, and it optimizes the parameters. So in that case we use the genetic algorithm and NSGA3 both to calibrate the driver behavior parameters and compare that which model actually works better. So that for arterial we calibrated the following parameters, driver behavior parameters, and these parameters were calibrated by using the objective function of travel time difference. We wanted to minimize the travel time difference from field and simulation, also the split utilization ratio and the throughput from field and simulation. We wanted to minimize this data using the objective using the optimization. When you use the genetic algorithm, we only use the travel time, but for NSGA3 we used all three of these objective functions to calibrate the driver behavior parameters. This is the step-by-step process of NSGA3. We initialize by creating the population, and we run the simulation for individual population. All of these were done by using COM interface, and we also then we take the output from the simulation and we compared it with the field data and get the fitness value. Fitness value was the main result of the objective function, and we run the NSG3 algorithm for like 100 generation, and NSG3 algorithm gives us the Pareto optimal solution. Like Pareto optimal solution is the trade-off between all of the objective functions, that which one we want to minimize. It is not a fixed value, but several values of the minimal function. So after that, we validated the BC model based on green occupancy ratio and percentage arrival on green later. So I wanted to show you the result of the Pareto sets from NSG3 output, that we got like 7 sets of Pareto optimals, which all have the minimum objective function value. Just one data is the trade-off between one to another. So we selected 2 of the set from the Pareto optimal to validate our results. So we have the set, these 2 sets have this function of objective function values, and the driver behavior parameters, and that also it is different from the default value that VSIM uses, because it actually calibrated for the field observation. And we also use the genetic algorithm for only travel time, and we have the value here and the travel time error, and also the driver behavior parameters for this algorithm. And the calibration model actually shows that the NSGS sets, NSGS set 1 and 2, especially 1, gives us better result in terms of error. It minimizes the error of the field data and the simulation data more. And genetic only, but in terms of travel time, genetic algorithm works well. But when we see the other parameters like split utilization ratio, genetic algorithm does not give us good result. In that case, NSG2 and NSG set 1 and 2 is better in terms of calibration results, and also in terms of validation result, which was based on green occupancy ratio and percentage arrival on green. We see that it's the NSG3 sets are giving us better results in terms of error in green occupancy ratio and percentage arrival on green. So this method actually uses the existing and emerging sources and optimization method to calibrate the VSIM arterial network. And this paper uses the microscopic signal timing performance measures for driver behavior parameter calibration, only the signal timing performance measures. And when we compare the single objective optimization with the multi-objective optimization, we say that we have lower travel time error for both of the cases, but multi-objective optimization gives us significantly lower error for high resolution controller traffic data measures, the performance measures. That is all. Thank you, everyone.
So hi everyone, my name is Qianwen, or I go by Cami. I'm a PhD student in the University of South Florida. Today I will be presenting our work entitled Lane Changing Model for Connected Autonomous Vehicles, or CAVs. This work is instructed by my advisor, Dr. Xiaopeng Li. This work was sponsored by Federal Highway Administration, FHWA. This is the outline for my presentation. The first thing I want to introduce is motivation. So traffic analysis modeling and simulation, or AMS tools, provide an efficient means to evaluate transportation improvement projects before deployment. However, the existing AMS tools are not well suited for evaluating CAV applications because the vehicle connectivity function is not properly represented. And for the CAV models, they are not realistic regarding the current CAV technologies. Most of them focus on longitudinal moment modeling, and but they cannot neglect the lateral CAV moment modeling. So we propose this mixed traffic simulation framework, this flowchart here, and the key component is the CAV lane change model, as highlighted in this shadowed figures here. I won't bore you with the details, but I do want to highlight some features that we propose. The first thing I want to introduce is called the cooperative state. This state is defined for CAVs. So if the CAV is uncooperative, then during a car following, sorry, the CF here means car following. So during a car following process, if the CAV is not cooperative, or we say uncooperative, the CAV will only follow the preceding vehicle in the current lane, regardless the lane changing signal or the preceding CAV is in the neighboring lane, as shown in the left figure. But if the CAV is cooperative, then in the CAV's car following, it will follows not only the current preceding vehicle 1, but also the preceding vehicle in the neighboring lane with the lane changing signals on, which is vehicle 2 in just this case, as shown in the right figure. And now we talk about the lane change. So a lane change for the CAV, it is initiated when the first two criteria are met. The first one is called the incentive criterion with respect to vehicle 1 and the vehicle 2. If this criteria is met, then the first criterion incentive check is met, which means the CAV can travel faster following vehicle 2 rather than following vehicle 1. And I want to point out this incentive criteria is only defined for discretionary lane changes. And the second criterion is called safety. It is defined with respect to CAV and vehicle 3. And it is defined for both mandatory lane changes and discretionary lane changes. Basically, it requires that it is safe for the CAV to make a lane change, and it is also safe for vehicle 3 to accommodate this lane change. If these two criteria pass, then the CAV will make a lane change to the target lane. And the safety criteria, as introduced before, are assessed continuously with respect to both CAV and vehicle 3. And if this criteria are met, then this lane change will continue. Which means the CAV will keep in the designated lane change trajectory and make the lane change. But if the safety criteria fails with respect to either CAV or the vehicle 3, if this fails, then the CAV will abort this lane change, which means it will, in this case, the safety criterion with respect to vehicle 3 fails, then the CAV will go back to its original lane. This is modeled for safety consideration. We actually, before this project, we did a field experiment, which is the CAV mandatory lane change, as shown in the below figures. So the lane change vehicle is the CAV, but all the surrounding vehicles are human-driven vehicles, vehicle 1 to 3. And we experimented 4 cases. So case 1 is to experiment shockwave in the current lane, as case 2 is shockwave in the target lane. Case 3 is all the vehicles maintain a relatively constant speed, and case 4 is a lane change abortion. So for each case, we have two sets of data. The first round data is used for the model calibration, the model that we just proposed, and the second round data is used for model validation. So for the model calibration, all the human-driven vehicle or HV's trajectories are controlled to replicate the field experiment data, but the CV trajectory is generated using the proposed model. And the calibration optimization objective is formulated as the sum of two terms. The first term is RMSE value of CV location, and the second term is error between the simulated lane change time and the observed lane change time. We use interior point method to find the optimal parameter values. Here is the results of case 1. We see the calibrated CV trajectory and the field observed CV trajectory are quite similar. In this figure, it is the pink curve and the black dash curve. And after the calculation, we see the vehicle location RMS value is only 1.86 meters. And this table is calibration result summary for all the 4 cases. After calibration, we move to model validation, which means we use the second round of the data to do the validation. Still, like the calibration, we control the human-driven vehicle's trajectory, but we generate the CV trajectory with the model. And we calculate CV location and the speed. The 2 figures below it actually are the validation results of case 1. So still, we see the observed trajectory. The pink curves are quite close to the black dash curve, which is the validated data trajectory for the CAV. So vehicle location RMSE is only 1.55 meters, and vehicle speed RMSE value is only 0.25 meters per second. And here is the summary of all the 4 cases. I also want to point out, like that, be compared with the model calibration results, the validation results shows a less difference, which means we conducted a valid model calibration. After we calibrated and validated this model, we conduct a case study and sensitivity analysis. We use a I-75 simulation segment. It is about 600 kilometers long, with 3 main lanes and 1 lane on-ramp and 1 lane off-ramp. We defined 2 zones. The first zone is called Zone A. It is mandatory lane change zone for all CAVs at on-ramp. And Zone B, it is a mandatory lane change zone defined for all diverging or say exiting CAVs. Diverging vehicles need to make mandatory lane changes until they reach lane 3. This is a screenshot of our simulation in PTVBSIM. Actually, we conducted a set of sensitivity analysis regarding various key parameters. Here, for the sake of time, I will only present the results regarding CAV cooperation rate. This cooperation rate was varied from 0, means no cooperation at all, to 1, means all CAVs will be cooperative. We see as this cooperation rate increase. Let me first introduce a few measurements. So we use 3 measurements. The first one is called average speed, which is an indicator of traffic mobility, and vehicle speed standard deviation, an indicator of traffic stability, and another mobility indicator, traffic flow rate. And the results show that as the CAV cooperation rate increases, the performance, both stability and mobility, first improves until the cooperation rate is about 0.5, and then the performance decreases as the cooperation rate further increases. The reason is that at the initial increase, more cooperative traffic increases the chances for the CAVs to complete lane changes, and thus the impedance from lane changes is reduced. But as the cooperation rate further increases, cooperative CAVs increase the average gaps between vehicles and thus may slow down the traffic. And we also want to point out here is because the CAV lane change model is calibrated with the data collected from a lab designed AV. So there might be a slight difference between the commercial available AV models. Actually, it is the CAV lane change study got us thinking. So what is difference between a human-driven vehicle following an AV with it following an normal human-driven vehicle? So to test this question, we conducted another set of experiment. So to see how human-driven vehicles react to CAVs or AVs. So in the baseline setting, we ask a human-driven vehicle following another human-driven vehicle, as shown in the first in the top figure. And in the experimental setting, we test two scenarios. The first scenario is a human-driven vehicle following a conspicuous CAV. So this CAV, as you may be able to see the red car here, it is assembled with external onboard sensor, and it has a flashing light on, indicating that it is in the AV mode. And in the second testing scenario, we ask a human-driven vehicle following an inconspicuous CAV. That vehicle looks just like a human-driven vehicle because you don't see any appearance difference, as shown in the bottom figure. The results show that in the first scenario, the conspicuous CAV scenario, human-driven vehicle behavior model might be different in the mixed traffic compared with the existing traffic, which means in the future modeling work, we may need, if the CAVs or AVs are apparently different from human-driven vehicles, we need to modify the human-driven vehicle car following behavior to be realistic. And in the second testing scenario, the inconspicuous CAV scenario, the existing human-driven vehicle for car following behavior can still be applied to the mixed traffic. But the limitation of this piece of work is that we only test vehicle car following behavior versus longitudinal behavior. And other experiments were tested in a test track setting. So we expect that more studies will be conducted in this field to validate the findings from this study. And this work was published by Transportation Research Part C, and it is forthcoming. So you can access to this work via the link provided below. And also we post our data on GitHub, listed in the bottom. Here are actually just my references. So as I stated from the beginning, this work is funded by FHWA. It is a project entitled Developing Analysis, Modeling, and Simulation Tools for Connected and Autonomous Automated Vehicle Applications. Basically, this project is integration of 4 different CAV applications, and our CAV lane change model is one of them. So this project report actually is forthcoming. It will be released anytime from now. From our side, our CAV lane change work entitled Simulation of Mixed Traffic with Cooperative Lane Changes just got accepted by the journal Computer-Aided Civil and Infrastructure Engineering. It is not published yet, but the preprint is available at ResearchGate via the link provided here. And also, we released our code at ITS Code Hub. Feel free to download and play with it. In the end, I want to thank you for all your time, and also, of course, thank you for the invitation to share our work with the public. And welcome to check our webpage, our YouTube channel, and our Facebook page to follow up on our research. And thank you.